and welcome to Ganesh Institute channel. So today we are going to discuss about topology. What is topology? So it is made up of two words, topo and logy. Obviously you know that logy is the study of something and here topo stands for a surface. So basically it is the study of surfaces. Now you might be thinking that okay, geometry is also the study of surfaces, study of figures, and what is the difference between geometry and this topology? So the basic difference is that we know that in geometrical form, if there is a circle and a square, then these are not equivalent, these are not similar. But in topology, we only consider the bases with the help of their elements, means what type of surface they are having, not the shape in which they are. Okay, we don't focus on that. So now in topology, if let's say we are given with a set, then what are the conditions that that particular set will be a topological set? And there are two forms of topological set: closed set and open set. So let's begin with an example. Let's say you have any set X in the form of AB. Okay, any non-empty set. Now, if I ask you that make a power set, means enlist all of the subsets of this particular set. So you know the set of subset is called power set, right? So that power set will be firstly phi, because null set is a set of any set, subset of any set. Thereafter your elements in different form and the whole set, right? You know the subsets, right? Subset means, let's say you have 1, 2 as a main set and you have 1 only, because 1 lies in A, so 1 belongs to A, so 1 belongs to A. This element is in set A, that's why it is the one having the element 1, the set which is having 1 is a subset of A. Okay, subset of A. Similarly, you can see that obviously null set is there. So phi is the subset of X, A is the subset of X, B is the subset of X, and a particular set is a subset of itself. So this is your power set. Now, if you want to check whether this power set, that means a set having all the subsets of X, right, is a topological set or not. So for that, for topology, particular set should be constrained within 3 conditions. First, phi and that element should be in that topological set, if it is a topology. Let's say it is tau. So, let's say, let us take an example of this only. Does this satisfy first condition? Is phi there? Yes. Is X there? X is AB. Yes. So first condition is satisfied by this set. Okay. Secondly, it should be, that topological set should have the union of finite elements in that. What does it mean? Let's say you have any two elements you can opt. Let's say you have A and B. And if you do the union of these elements, then what will you get? AB. And it is in that particular set, right? So it satisfies the second equation. For instance, let's take another example, phi and A. If you do the union of phi and A, then what will you get? Phi is nothing, A. And A is in this set. So, second condition says that union of all the elements, all the finite elements, any of these 2, these 3, should be in that set. Okay? And third is intersection of those finite sets, let's say it has 1 to n, any number, any element, and this is in the form of AI, A1, A2. So, what does it mean? Intersection of A1 and A2, A2 and A3, A3 and A5, anything lies from 1 to n. Okay. That intersection should also belong to that particular set which is claiming that it is a topological set. What does it mean? So let's begin. Again, this example, if you consider any these two elements of this particular set, let's say A and B, okay? So, these two elements, take the intersection, there is nothing common, so the intersection is phi. Does it contain phi? So, phi is there. So, phi belongs to T. That means it is satisfying. Let's take another example, phi and B. Phi and B. What's the intersection? What is the common thing in between phi and B? Nothing. Phi, right? So, that is also. Again, take B and intersection of B and AB. What's the common in between these two? B, which is also in T, in tau. That means it is holding all these three properties. Let me remind you. So first property is phi, and that set, that non-empty set, that finite set should belong to that particular set which is required to be proved as topological. Union of all the finite elements in between these, union of any of these elements of this topological set should be in it. Okay? If you want to check whether this set has any topology or not, so you need to check these three conditions, intersection as well. If it is following these three conditions, then that is topological set. Alright? And topology is this. Okay? Now, there are two types of this topological set. One is closed, one is open. So, let me tell you what is open set. For example, let me grab a cluster. So, let's say there is another set which you want to check whether it is closed or open. You have another set which is, let's say, A. Okay? Any other set which is a subset of your main non-empty set. Okay? Obviously, this A belongs to X, so this is a subset of X. This U is a subset of X. Okay? Now, you want to check whether this U is a closed or open topology. So, what you need to do, if this U following all the properties of topological, this A lies in T, right? Lies in tau. So, this U, because lies in tau and following all those three properties, so this is open set. Okay? Thereafter, if you take the complement of that particular set, so this is A, this is extracted from X, because we have taken U is a subset of X, right? If you take the complement of this, complement of A is, that means not A, which is B, right? And B also belongs to that topological set, right? That's why it is closed. Alright? So, this set U is both open and closed. That's why it can also be called as clopen. Okay? If it would not belong to tau, then it would not be an open set, not be a closed set. So in this way you can check it out. I hope you understand this video, and if so, then don't forget to like, share and subscribe my channel. Till my next video, take care of yourself. Bye bye.